In this video, we'll talk about Green's theorem. Green's theorem gives us a way to calculate line integrals of the form f dot dr over simple closed curves. So Green's theorem states the following. Let C be a piecewise smooth simple closed curve with positive orientation, and let R be the region enclosed by C. Let F be the vector field with components m and n. Then the line integral of f dot dr over the curve C can be evaluated by doing a double integral over the region R of the partial derivative of n with respect to x minus the partial derivative of m with respect to y. In this video, we'll give a rough idea of how this theorem is proved, and then in our next video, we'll go through some examples of how this theorem is used. I want to start by looking at this theorem on a rectangle. So imagine that I have a rectangle with initial point x1, y1. Let's say I then go to the point x2, y1. Then I go up to the point x2, y2. And then go to the point x1, y2. And then finally I return to the point x1, y1. This is going to be our curve C. The region enclosed by C I'll label as R, and that's our rectangle. Now our curve C has four pieces, which I'll label as C1, C2, C3, and C4. So if I want to calculate the line integral over the curve C of f dot dr, I can do this by breaking it apart into the four pieces. For now, I'm going to concentrate on two particular pieces, the integral over C1 and the integral over C3. To evaluate these line integrals, I would need a parameterization. For the curve C1, I can parameterize this using R of t equals t, comma, y1, where t goes from x1 to x2. For C3, I can parameterize this in much the same way. I have R of t equals t and y2. This time, I'm going to say that my t goes from x2 to x1 because I'm going backwards. So if we just look at the line integrals over C1 and C3, we have integral from x1 to x2 of m dx. Well, m, plugging in our parameterization, will look like m of t comma y1. dx is x prime of t dt, but in our case, x prime of t is 1, so we have times 1 dt, and then we have plus n dy. But notice that dy here is y prime of t dt, but in our case, y is a constant. It's the constant y1, so y prime of t is 0. So we don't need this term at all. Then we want to add the line integral over C3. That's going to be the integral from x2 to x1 this time. Again, m dx is going to look like m, and then plugging in the parameterization, I have t comma y2. dx, again, is going to be times 1 dt, because x prime of t is 1. Then, again, I don't have the plus n dy part because in our parameterization, the y component is constant, so y prime of t is 0. So I have the integral from x1 to x2 of m t y1 dt. Here, in my second integral, I'm going to swap the limits of integration and write this as minus integral from x1 to x2 of m t y2 dt. Combining the two integrals together, I have integral from x1 to x2 of m t y1 minus m t y2 dt. Now what I want to do is compare this to the double integral over the region R. Specifically, I want to look at the double integral over the region R of the partial derivative of m with respect to y dA. The double integral is over a rectangle, it's pretty easy to set up. I'm going to integrate in the order dy dx. So I have integral of partial derivative of m with respect to y dy dx. My y's will go from y1 to y2, and my x's will go from x1 to x2. So let's start by performing the inner integral. So I have integral from x1 to x2. By the fundamental theorem of calculus, the integral of partial derivative of m with respect to y dy is just going to be m evaluated at the endpoints y1 to y2, and all of this dx. So that's going to be integral from x1 to x2 of m xy2 minus m xy1 dx. Now notice the similarity between this integral and this integral. There are some slight differences. In my line integral, I have the variable t instead of the variable x, but that doesn't matter because I can use any variable that I want. The other difference is that I have m of t y1 minus m of t y2 in my line integral. On the other hand, in my double integral, I have m of xy2 minus m of xy1. So the two line integrals are just off by a negative sign, meaning I can write the sum of the line integrals over c1 and c3 equals the double integral of negative of partial derivative of m with respect to y over the region R. If we repeat the process over the curves c2 and c4, we get a similar result. The sum of the line integrals over c2 and c4 is equal to the double integral of the partial derivative of n with respect to x over the region R. Putting those two parts together, we see that on this rectangular region, Green's theorem is true. We have that the line integral of f dot dr is equal to the double integral of partial derivative of n with respect to x minus the partial derivative of m with respect to y over the region R. Now we want to generalize this theorem for curves of different shapes. Now suppose that I have two rectangular regions side by side. Let's label the first region R1 and the second region R2. Now let's consider the sum of the double integrals over the region R1 and over the region R2 of the partial derivative of n with respect to x minus the partial derivative of m with respect to y. We've proven that Green's theorem holds over rectangular regions, so this sum of double integrals can be rewritten as the sum of line integrals over c1 of f dot dr plus line integral of c2 of f dot dr, where c1 is the boundary of region R1, so it's this curve right here, oriented positively, and c2 is the boundary of the second region, so it's the curve that looks like this. Again, if I orient this positively, I would get something like this. Let's label some of the line segments in our curve. Let's label this first one L1, then here L2, L3, L4. Then on my second curve, let's label this L5, L6, L7, and then L8. So we notice that the line segments L2 and L8 are the same line segment, only they're just going in opposite directions. When I add up the line integrals over the curve C1 and over the curve C2, I get the following: the sum of the line integrals over each segment. Now the line integral over L8 can be rewritten as negative of the line integral over L2 of f dot dr because they are the same line just going in opposite directions. So I can cancel this term out with this term. So in the end, this is the line integral of f dot dr over the segments L1, L3, L4, L5, L6, and L7. If we look at these remaining line segments, we have the following picture. So when we sum up the double integral over region R1 and R2, we end up with the line integral over the boundary of R1 union R2 of f dot dr. Now let's suppose that I have a curve C that's not in the shape of a rectangle. What I can do is overlay a grid on top of this curve. Then let's consider the rectangles that are fully enclosed within our curve C. Since we've proven Green's theorem to be true for rectangular regions, we have the following. The double integral over the shaded region of the partial derivative of n with respect to x minus the partial derivative of m with respect to y is equal to the line integral over the boundary of that shaded region of f dot dr. Now what we can do is take a finer grid. With this finer grid, our shaded region is now a better approximation to the region enclosed by the curve C, and the boundary of this shaded region more closely approximates the curve C. As we take the limit as the grid gets finer and finer, our shaded region will become the entire region R bounded by the curve C, and the boundary of it will be our curve C. And this gives us Green's theorem for any simple closed curve. In our next video, we'll go through some examples of how we use Green's theorem to calculate line integrals over simple closed curves.